Let's begin with the question on circuits, which falls under AP Electricity and Magnetism. So here we have a depictive circuit. From initial observations, we notice that the circuit presented has two junctions where currents are seen to be flowing and KCL equations can be written. And it seems to have two loops where your KVL equations can be written. The circuit shown above is constructed with two 6-volt batteries and 3 resistors with values shown. The voltages shown don't seem to have internal resistances, and we assume them to be as such. The currents I1 and I2 and I3 in each branch of the circuit are indicated. Part A, subsection 1, using Kirchoff's rules, write but do not solve the equations that can be used to solve for the current in each resistor. Here, we can use Kirchoff's current law applied to either one of the junctions indicated here. Kirchoff's current law says that the sum of currents entering a given junction is equivalent to sum of the currents exiting a given junction. Here we notice that I1 and I3 seem to be entering the junction, while I2 seems to be exiting the junction. So we have I1 plus I3 is equivalent to I2. This gives us the KCL equation necessary to help solve the question. Moving on, calculate the current in the 200 ohm resistor. To calculate the value of current I2, which is indicated in the circuit diagram, we will have to make use of KVL equations, and let's start writing them. The simplest way to write KVL equations is to start off by giving polarities, since currents are already imagined. Polarities for voltage sources are predetermined, whereas for resistive components, the polarity is given such that current enters a positive polarity and exits a negative polarity. Now, we can start from the top left corner for the first loop and go clockwise, and we start to write our equations. Plus I1 times the resistance, that is 150 ohm, going ahead, plus I2 times the resistance 200 ohm, minus the voltage 6 volt, gives us back to our original point, giving me the total change in EMF, voltage, and potential difference as stated to be 0. This is Kirchoff's voltage law. The same can also be written for the loop 2. We again start from the top left corner, going clockwise. We start with minus I3 times 100 plus 6 volt minus I2 times 200 gives us the equivalent of 0. Here we notice that we in fact have a system of linear equations. Please use the calculator function to find the values of the individual variables. And when computed as such, you get the value of I2 to be exactly equal to 0.023 ampere. Moving ahead, part 3 asks us to calculate the power dissipated by a 200 ohm resistor. Here, for the 200 ohm resistor, we have the value of its resistance R to be equivalent to 200 ohm, and its current I2 is found to be 0.023 ampere. Power for a resistor is defined by the formula P equals I square R. Substituting the value of I as 0.023 and R as 200, we get power dissipated to be approximately equivalent to the value 0.107 watt. Moving on to the last question. Here, we notice from the circuit that the two 6-volt batteries are replaced, and one of the batteries is replaced by an unknown EMF of value epsilon, and another by a known value of resistor whose resistance is 50 ohm. As shown above, the voltmeter V shows that the voltage across the 200 ohm resistor is 4.4 volt. Calculate the current through the 50 ohm resistor. Now, we have a lot of information to be disseminated here. We understand from the circuit diagram that these two resistor components do not have any active component between them, and hence their equivalent resistance can be found out. The two resistors seem to be in a series combination, and equivalent resistance R in a series combination is given by R series is equivalent to R1 plus R2. Doing as such, we get the combined resistance between the 100 and the 50 ohm resistors to be 150 ohm. We'll replace the circuit with an equivalent circuit with the resistances combined. The EMF is still unknown at a value epsilon. There is a resistance of 150 ohm here. There is a resistor whose voltage is known to be 4.4 volt, and this resistance is 200 ohm. We know that the voltage across these two terminals is 4.4 volt. We also have the third resistor, which is a combination of the two resistors as stated before. This is 150 ohm. We notice that for the 200 ohm resistor, the voltage V is known as 4.4 volt. Since the terminals for the 200 ohm resistor and the 150 ohm resistor seem to be the same, the 150 ohm resistor also has an equivalent voltage V equal to 4.4 volt. This is further substantiated by the fact that the two resistors 200 and 150 ohm appear to be parallel to each other, and thus must and should have identical voltage. We can find out the current by using the formula current I is equal to V by R. Current I is equal to the voltage V divided by resistance R. Voltage V is 4.4, while the combined resistance as found before is 150 ohm, giving us the value of current here to be exactly equal to 0.029 ampere. 0.029 ampere. Moving ahead, we have also been asked to figure out the voltage epsilon of the battery. Here we notice that since the 150 ohm resistance is a combination of the 50 and the 100 ohm in series, the current through each one is still 0.029 ampere, while the current through the 200 ohm resistor can be found out using the same formula, although by different substitutions, as 4.4 divided by 200. This value turns out to be about 0.022 ampere. We understand that the current flowing here is 0.022 ampere, while the current flowing here is 0.029 ampere. The current that is flowing here can be understood to be the summation of the current flowing here and here by applying KCL at this junction. So the main current, or the main branch current, can be found out as I total, which is equal to 0.022 that is flowing through the 200 ohm resistor plus 0.029 which is flowing through the combination of the 100 and the 50 ohm resistors. The total current sums up to be 0.051 ampere. The total resistance can also be found out. As you stated before, the 150 ohm resistor and the 200 ohm resistor appear to be in a parallel combination. So R parallel is given by the formula. R parallel is equal to R1 times R2 divided by R1 plus R2. Using this, we can find out the total value of resistance as R total is equal to the parallel combination of the two resistors, that is 200 and 150, as 200 times 150 divided by 200 plus 150, which is 350. This equivalent resistance, that is of the three resistors, can be further added to the value 150 ohm, since this entire combination of the three resistor system is in series with the 150 ohm resistance. So this entire value is again added to 150, giving us the value of total resistance when simplified as 236 ohm. Since we have the value of total current and we have the value of total resistance, and more importantly, we just have a single active component or an active energy supplying voltage source, epsilon, in the circuit, we can find out epsilon finally as epsilon is equal to I total times R total. This gives us the value of epsilon to be approximately 12 volt. This concludes the solution to this question. Thank you.